colder than Antarctica and under pressure strong enough to cross steel in seconds. This hidden world covers most of the planet, yet remains largely unexplored, not because it is unimportant, but because it is extremely difficult to reach. Exploring this environment requires machines built to survive conditions no human body can tolerate, and this is where unmanned underwater vehicles become essential tools for marine discovery. As depth increases, the ocean undergoes dramatic changes in temperature, pressure, and light availability. Below a few hundred meters, sunlight disappears completely, creating a permanent state of darkness known as the aphotic zone. Temperatures approach freezing levels, while pressure increases by 1 atmosphere every 10 meters, reaching thousands of atmospheres in the deepest trenches. Despite these extreme conditions, life persists, evolving unique adaptations such as bioluminescence, slow metabolism, and pressure resistant biological structures. Understanding this environment requires tools capable of long term survival and precise observation. Human exploration of the deep ocean is limited by biological constraints and high operational risk. Even the most advanced manned submersibles can only reach certain depth for limited durations. Unmanned underwater vehicles eliminate these limitations by replacing a human presence with robotic endurance. These systems can descend deeper, remain operational for extended periods, and perform repetitive or hazardous tasks without risk to human life. Their deployment has transformed deep sea research, making systematic exploration both safer and more efficient. Unmanned underwater vehicles are engineered to stand with one of the hardest environments on Earth. Their structures are typically built from titanium alloys or reinforced composites to resist extreme pressure. Internal electronics are housed within pressure resistant enclosures, while propulsion systems are optimized for efficiency and stability in dense water. Advanced navigation systems combine inertial sensors, depth sensors, and sonar to maintain precise positioning in complete darkness. Every design element serves a single purpose: reliable operation in an environment hostile to conventional technology. To perceive the deep ocean, underwater vehicles rely on a combination of imaging and sensing technology. High sensitivity cameras capture visual data under artificial lighting, revealing organisms and geological features never seen before. Sonar systems generate detailed maps of the seafloor by emitting acoustic waves and analyzing their reflections. Additional sensors measure temperature, salinity, chemical composition, and magnetic fields, allowing scientists to study both biological and physical processes. Together, these systems convert an invisible world into measurable data. A deep sea mission begins at the surface, where the unmanned vehicle is launched from a research vessel. As it descends, onboard systems continuously adjust buoyancy, orientation, and trajectory. Communication with the surface is maintained through acoustic signals or tethered connections, depending on the vehicle type. During the mission, the robot follows a pre-programmed route or adapts autonomously to an unexpected terrain. Every movement is calculated to maximize data collection while minimizing energy consumption and mechanical stress. Unmanned underwater vehicles have led to groundbreaking discoveries across multiple scientific fields. They have revealed ecosystems surrounding hydrothermal vents, where organisms rely on chemical energy rather than sunlight. They have documented ancient coral formations and identified previously unknown species with unique evolutionary traits. Geological surveys conducted by these robots have mapped underwater volcanoes, fault lines, and trenches, improving understanding of Earth's tectonic activity. Each mission expands knowledge of how the planet functions beneath its surface. Operating in the deep ocean presents constant challenges. Extreme pressure threatens structural integrity, while low temperatures affect battery performance and electronics. Navigation is complicated by the absence of GPS signals, requiring alternative localization methods. Communication bandwidth is limited, restricting real time data transfer. To address this issues, engineers integrate repeatedly fault tolerant systems and advanced software capable of adapting to unpredictable conditions. Success in deep sea robotics depends on precision, reliability, and resilience. Advancement in artificial intelligence and materials science are shaping the next generation of unmanned underwater vehicles. Future systems will possess greater autonomy, enabling them to analyze data and make decisions during missions without surface intervention. Coordinated fleets of vehicles will map large areas simultaneously, increasing efficiency and coverage. Bio-inspired designs will enhance maneuverability and energy efficiency. These developments will push exploration deeper and further, bringing the deep ocean into clear science focus. So, as we rise back to the surface, remember this: the deep ocean is not just water beneath your feet, it is a world of wonders, a reservoir of secrets, a universe of unknowns waiting for us to explore. And unmanned underwater vehicles, these robotic explorers, are the key that unlocks it all. With every dive, they shine light where darkness has ruled for millions of years. This is technology, this is science, this is adventures, this is the Career Robotic channel, and this has been your dive into the abyss. If you loved this journey, smash the like button, subscribe, and join me for more robotic missions into the unknown. Until next time, stay curious, stay inspired, and keep creating. Goodbye.